What's up, everybody? Welcome back to the Mathnasium. I'm Mr. Schlegel. Today we're going to learn about functions. If you missed the lesson, you're in the right spot. Time to do the lesson here with the video. Okay. So a function in mathematics is just like a vending machine. Vending machines have inputs. Functions have inputs. The input for the vending machine is the code, right? So you put a code in, and out pops a snack. So we have our output. Okay? We have our inputs, we have our outputs. The output is the snack, delicious snack we get from the vending machine. All of them are delicious except for this crummy apple. What? You put an apple between two pastries? What the heck's wrong with these guys? It's going to fall, get bruised. Big mess. Who made this vending machine? I'm furious. Okay. Inputs, outputs, code, snack. Makes sense. Let's keep cruising. All right, so the notes for this assignment, you can get the blank notes on my website or in Google Classroom. We're going to go through and kind of read these together, and I'm going to talk about what I mean by them. Prominent theme of the class will be the idea of a function. Today we'll start by defining a function very generally and reviewing function notation. Throughout the year we will explore different types of functions which can be used to model different real-life phenomena. So a blank is a set of ordered pairs. So we call a set of ordered pairs or a connection between numbers a relation. This is a relation, okay? So anytime you have a collection of ordered pairs, that is called a relation. Now, let's go ahead and take that first relation that's in your notes today. The first relation being 0, 2, 0, 2, 1, 3, and 2, 4. Oops, forgot my parentheses there. And then we'll do our brackets. Fantastic. All right. Now, you can represent a relation like this in many different ways, okay? And those ways that we can represent a relation are through a set. This thing right here is called a set. It's written in set notation, okay? The other way you can represent something like this is also, it's their points. So you guys might immediately think, hey, I can write this as a graph. That is also an option. We can graph these things. That's fine. We can also represent them as a table. Some people know them as t-tables. You may have seen those before, and they're pretty commonly used. So you put x and y. Ordered pair has an x value, a y value, right? 0, 2, 1, 3, and 2, 4. So you can represent it as a set, a graph, a table. You can also represent it as a couple other things that you may have seen as an equation. Not all relations can be represented by an equation. Sometimes they can. So I'm going to put a little star right here, and I'll say sometimes there's an equation or a rule that can describe the relationship between the set of points, but not always. Another quick comment is this is a finite set. It has 3 ordered pairs. There are also sets that have an infinite number of pairs, and typically those are tied to the ones that are tied to equations, okay? So here we have our relation. The other one that we're going to learn about, or maybe refresh ourselves, is called a mapping. A mapping is just kind of a way to connect the numbers, all our x values and our y values. And there's a nice segue. Turns out the x values and the y values have a name. If I were to write all these points or all the points in my relation on a piece of paper, and then I were to cut them in half and put all the x values in one hat and all of the y values in a different hat, the hat with all the x values, we call that the domain of the function, okay? It's all the inputs. And then the hat with all the y values, that's called the range. Hat with all the y values is called the range. So the domain is all our x values. The range is all of our y values. All right, and we'll kind of talk about that with this specific example in just a minute. It turns out, though, we're making a mapping first, sorry. So to create a mapping, it's actually really simple. You draw two kind of ovally shapes here, and you write all the possible x values. I'm going to do them in numerical order. That just is what makes most sense to me. So I'll do 0, 1, 2. This is our domain. The domain is written on the left. Come on. There we go. Domain is written on the left. The range is written on the right. And the range is 2, 3, 4. And what makes a mapping is you have your elements of your domain. Each one should only be written one time. You have your elements of your range. Each thing should only be written one time. And then you draw the arrows, right? The domain is going towards the range. 0 is connected to 2. 1 is connected to 3. 2 is connected to 4, right? Goes to 4. These things are linked because they are ordered pairs. Now, the reason we do a mapping is when things get interesting is when elements of the domain or elements of the range are reused, or maybe a point has or one of those elements is present in 2 different points or 2 different ordered pairs. Okay, so here we have our domain 0, 1, and 2, and our range 2, 3, and 4. Okay, so here's the thing that's crazy, okay? I just told you what a relation was. Well, there's this other thing that is a kind of a relation. It's a special kind of relation. We kind of already mentioned it. It's called a function, okay? Function is our mathematical vending machine. A function is a relation in which each element of the domain is paired with exactly one element in the range. Each input only goes to one singular output, exactly one output. Something fails to be a function if it has one input has more than one output. Could be 2 or more. As soon as we identify that, it fails to be a function. Okay. Let's see here. So why is this a problem? Let's think back to that vending machine, right? We're talking about the vending machine. It would really suck for the company that stocks the vending machine if you could plug in a code, right? If you could plug in a code and 2 snacks fell out. That would not be good for the vending machine company. You want the code that is labeled under the tray to spit out the snack that's in that tray. Now, it is possible in a vending machine for multiple trays to have, the same snack. That's okay, but there are 2 separate codes going into the vending machine that are associated with those nacho cheese Doritos. Just a fun fact there. Another fun fact, Cool Ranch Doritos in Europe are called Cool American Doritos. Chew on that. Those little red and blue specks. Okay, yeah, we talked about the different ways they can be represented. Okay, yeah, can you think of a function that has 2 different inputs result in the same output? You may have seen one in Algebra 1. There's some pretty famous ones. Maybe not, who knows? There's one that went through these 2 points. You can try and guess the name. Anything that was like a quadratic. These kind of functions, there would be 2 inputs that would have the same output, right? Just like 2 trays can have nacho cheese Doritos in the vending machine. That's okay. Still a function. That is just fine. This is a quadratic or a parabola. Is this predictable? Yes, because every input has a place to go and only one place to go. Okay, one thing I want to say really quickly is that if this is the collection of all of our relations, let's say this is every single relation. Not all relations are functions. Only some relations are functions. Okay, so that's important to keep in mind as we move forward. All right, so we're going to take a look at these 2 mappings. We're going to write them out, and then we are going to determine whether or not they are, the two relations we're going to determine whether or not they are functions. So let's start by identifying the domain and range. Now, I'm not going to write domain and range out every single time. I'm going to put a D for domain and an R for range. You might want to write those in your notes so that you don't forget what that means, what D and R stand for. Okay, 2, 3, 4, 7 is, I'm looking at all the X values. 2, 3, 4, and 7 are all the X values that form the domain. And the range, and I'll do this in numerical order, there are only 3 of them, 5, 6, and 7. 5, 6, and 7. Oh, sorry, take that back. 5, 6, and 8. 5, 6, and 8 are the elements of our range. Okay, so now we create our mapping. Notice how I didn't write 6 twice, right? I only wrote it 1 time. That's really key. 2 goes to 6. 3 is mapped also to 6. 4 is mapped to 5. 7 is mapped to 8. Now, we've created our mapping. Is this a function? Is this a function? Let's go back to our definition. What's that definition? Function is a relation where every input, each element of the domain is paired with exactly one element of the range. Is that true? Yeah. Yes, that's true. Okay, these are our codes for the vending machine. These are the snacks. Can one code give us back, or can 2 different codes give us the same snack? Is that allowed? That's okay. Okay, so this is a function. Because, okay, each input has exactly one, come on computer, exactly one output. Now, you have to put the word exactly in there. You have to put the word exactly in there for the following reason. It's like saying how many months have 28 days? Well, all of them have 28 days. How many months have exactly 28 days? Only one, right? So if you say exactly, that makes a big difference. Okay, you guys can try this one on your own. Pause the video and then start her back up when you're ready to check your work. Okay, here we go. All right, we got our domain, which is very oddly shaped. We got our range over here. Let's line her up. My computer is struggling. I'm going to see if I can get one that's a little bit quicker. Elements of the domain, there are 3, -1, 0, and 1. Elements of the range, there are 3, -3, 7, and 10. And again, I'm putting them in numerical order from lowest to highest. Maybe that's weird. I don't know. Okay, let's connect them. -1 goes to 7. 0 goes to -3. 0 also goes to 7. And 1 goes to 10. Is this a function? The answer is no. This is not a function. Be specific. Not a function. Come on, computer. Boy, howdy. This baby's struggling. There we go. Not a function. Not a function. Okay. Exclamation mark. You got to yell it and not forget letters in the middle. Okay, this is not a function. Why isn't a function? It's not a function because the input 0 is the problem. It's not a function because 0 is oh my gosh. Computer, 0 is connected to, or rather, 0 goes to two outputs. Hooray, 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 hooray. Yep, 0 goes to 2 different outputs. Bingo. All right, super. Not a function because 0 is the problem. You look, all you have to do is look for an element of the domain that goes to multiple elements of the range. And then you'll know that it's not a function. All right, let's keep chugging along. So let's think really quickly. We know that if an element of the domain goes to multiple elements of the range, one single element of the domain or one single x value, that it's not a function. But I also told you that these relations and functions can be represented in many different ways, right? Tables, mappings, graphs. The easiest ones to see it on are mappings and graphs. Easiest way to tell whether or not something's a function, right? With a mapping, this goes to 2 places. With a graph, what does that look like? Well, you're going to have 2 points with the same x value. If they have the same x value and different y values, right? Same x value, they're going to be above one another on the coordinate plane. So it was devised a test called the vertical line test. If I can draw a vertical line through 2 points on a graph, then we know that that can't be a function because that is one element of the domain or one x value that goes to 2 different y values. Okay? If any line passes through the graph more than once, the relation is not a function. Okay, we kind of talked about why it worked. All right, let's take a look at these two. Okay, first thing I hear from students, usually they're like, oh, I got it. Bingo. Not a function, I did it. Hold on. It's the vertical line test, not the horizontal line test, right? So, draw your vertical line. It's not perfectly vertical, but it's good enough. Now, if you drag this line around, is it possible for it to travel through the graph more than once? No, it never will. It will never travel through more than once. Okay? So, that means this is, oh, come on, computer. There we go. That means this is a function. Hooray! Because it passes the vertical line test. Okay, how about this bad boy? If I draw a vertical line, can I make it pass through more than one time? Absolutely. If you draw it anywhere between here and here, not only does it pass more than once, or pass twice, it passes 3 times. You technically could make it pass twice if you made it pass through the very end point in here, but all you have to do is say this is not a function because it fails the vertical line test. Not a function because it fails the vertical line test. That is justification enough, and I know that that's not perfectly vertical. It's also not directly at 1, but 1 is a spot where it fails. It passes through our relation. It passes through our relation 3 times. So it's not a function, and the reasoning there is you can say it's not a function because the input 1, just pick any of them that fail, has more than one output. Okay, next thing is function notation. Function notation. On the fringe case that we have a relation that can be expressed with an equation, oftentimes we use function notation to indicate that that is indeed, it is a function. So what are some reasons that we do this? Because this kind of stuff is what makes people hate math. Their teacher's like, all right, guys, we're going to learn about y equals mx plus b today. And then later they're like, I'm not going to use y anymore. Guys, don't mind me. I'm going to use f of x equals mx plus b. F of x equals mx plus b. And people are like, why don't you just use y? That's stupid. I'm out of here. Math is so hard. Blah, blah, blah. That's what they do. Okay? I've heard it 1,000 times. It is confusing. You have every right to be frustrated when a teacher does something like that, but it turns out it's for good reason. Okay, good reason. Function notation does a lot of things for us that I really like. Things that I like, first of all, it's really useful is it gives the equation a name. I'm about to give my computer a name because it's so bogged down. It cannot handle all of the things that are happening. Okay, it gives the equation a name so we can reference it quickly and we can compare. So we can use its name to compare other equations that are floating around, you know. Really, f of x and y can be used interchangeably. This doesn't mean multiplication, it's the name. It's saying we have this function named f, right? Its name is f, and f takes inputs, like, right? F takes inputs that are x values, and it spits out some number, right? And it turns out that they're in a line because it says mx plus b. But it gives a name to the equation so we can make comparisons between other functions. Ooh, look how f differs from g of x or something along those lines. I'm going to make a g of x, okay? Let's say g of x is a line. Let's say it's 4x plus 3. All right? We're going to say it is 4x plus 3. It also allows us to ask questions easily. It allows us to ask questions easily. Okay. Here's my example, and maybe I'm going into too much detail here, but I just get so stoked. Functions just get me pumped, okay? When I write, that should be an equal sign right there. When I write, for example, this, g with a 3 next to it, this doesn't mean g times 3. I mean, it can in certain math equations. It's all about context, though. You got to be able to read the context. Okay, if I say g of 3, by the way, this is red. You read this g of 3. If it's red g of 3, then this asks a question. What is that question? The question is as follows. This asks the question. Got to know what it asks. It asks the question, holy Moses. What is the value? What is the value of my function g when x equals 3? Oh my gosh, it's getting like half of them. This is so brutal. What is the value of my function g when x equals 3? Now, this is a pain to say every time. So mathematicians, we want a way that we can ask these kind of questions quickly. Now, functions in general in mathematics, comparing them and talking about them is, I guess, not a super common happening. The real place that I see them the most is in computer programming. Oftentimes you'll give a name to a function and you'll spit things in and out of a function very quickly. So thinking like a computer, function notation is very important, okay? I've been on this slide for too long. It's time to keep moving. So we can ask these questions and we can do these quick calculations. So we're going to have some practice with function notation now. Let's take a look. All right, all you do to evaluate something in function notation, when it says this f of x and you're finding f of 4, we're taking 4, it is an input into our function. It's going into our vending machine and it's going to spit something out when we're done. Okay, what does our function do to the number 4? Well, it multiplies it by 3 and then it adds 7. So we're going to come down here and we'll say f of 4 equals. Now, when I'm going to plug in, the first step requires no math at all. You just do 3 times, you leave empty parentheses, plus 7, and then you go through and you plug in your 4 afterwards. Okay, now you have to do order of operations. So in this case, we'll do 3 times 4 is 12. Then we can do addition first. Order of operations, please excuse my dear Aunt Sally, or however you learned it. Your groupings first, parentheses, brackets, square roots, absolute values. You have to simplify inside those first. So start on the inside, work your way out. Then exponents, then multiplication and division, then addition and subtraction. 12 plus 7 is 19. So what is the value of my function f when x equals 4? The value is 19, and this represents a point. This can be plotted. This represents the point 4, 19. All right, let's take a look at g of -2. G of -2. Plugging that baby in. That's 2 times -2 minus 4. I forgot my squared. Minus 4 times -2 plus 5. 2 times -2 minus 4 times -2 plus 5. 2 squared is 4. Exponents must happen first, right? So we have to do our exponents before we do any of the multiplication or division. So -2 times -2 is positive 4. Then we can go through, after we've done this step, now we can go through and do all of our multiplication. We have 2 times 4, and we have -4 times -2, which will result in 8 plus 8 plus 5. This is 16 plus 5, which is 21. Fantastic. All right, let's take a look at a couple other functions here. A couple other functions. You guys can pause the video and try these on your own if you'd like, or you can just watch along and write along with me. Let's find the value of our function f, who takes an input named r, and it spits it. What does it do to it? Well, it looks like you take the difference, the square root, and then another difference. So our function f, let's go ahead and plug this baby in. We're going to plug in -24 into our function f. So let's do that right now. Remember, the first step requires no math at all. We're just doing 25 minus, and then we always use parentheses when we substitute in. -24 outside the square root is a -6, so just be careful of that. All right, coming through, 25 minus -24. Opposite of -24 is positive 24. So this turns into 25 plus 24 minus 6, which is the square root of 49 minus 6. Remember, you got to simplify inside first and then work your way outward. We can't subtract because this -6 is outside the square root. We got to simplify inside any sort of grouping first. The square root of 49, what number times itself is 49? That's 7. 7 minus 6 is 1. 1. Come on, computer. Stick with me here. Okay, let's go through this next one. That is f of 3. F of 3 is equal to 5 times. Now we have these vertical bars. These are absolute value bars. Absolute value means how far is the inside of this thing away from 0? Well, we can't determine how far x squared minus 10x plus 2 is because we don't know what x is. So if you want to evaluate the absolute value, you got to simplify the inside verse, and then we'll know how far it is away from 0. So inside these bars, and I'm probably going to need to move this over just a smidge. Inside these bars, we're going to put, everywhere there's an X, we're putting parentheses, empty parentheses. Takes no math at all to do this. You just go through and put empty parentheses in there. +2 in bracket. Now I'm going to go through and put a 3 in every slot there. Okay, you can't distribute the 5. You can't multiply the 5. You got to simplify this inside of this grouping first. So forget about the 5, kind of forget about the absolute value bars for now. They're going to come down to the next step, but we're not going to do anything with them. So inside here, we're going to first do our exponent, right? Inside the grouping, exponents are going to happen first. 3 squared is 9. We can actually multiply the 10 and the 3 because they're separated by, addition and subtraction, and that's happening last anyways. So this is going to be -30 + 2. Okay, that's not a 1. Remember, this thing over here is an absolute value bar that is connected, or rather associated with this. All right, and so now we need to know what 9 - 30 + 2 is. I teach integers like good guys and bad guys, forces of evil, forces of good. We have 30 bad guys, and we have 9 + 2 good guys. Positive numbers are good guys. Negative numbers are bad guys, right? So 11 good guys are fighting 30 bad guys. Who's going to win? Well, the bad guys are going to win, and they're going to win by 19. So inside the absolute value bars, we have -19. The bad guys win. Now remember, now we've gotten this to just a number. What's the absolute value of -19? It is how far away -19 is from 0. And distance is always positive. So this is 5 times 19, which is 95. Okay, and the very last section here is using a graph. So sometimes it's not always a rule. You just have to look at a graph and be able to identify what it's asking. Remember, this asks a question, g of -4. You can refer back to the question that I wrote in quotes earlier. G of -4 asks the question, what is the value of my function g when the x value is -4? So all you have to do is trace over to -4 and then look at how high up it is. Where is it at? Oh, it's over here at 2. Okay, g of 2, where's g of 2? Well, you look at the x value 2, where's my function at? Oh, it's down here at -2. Oh, come on. That's an equal sign. Should be one showing up down here, hopefully. Apparently not. -2. Okay. G of 10, we kind of have an arrow continuing on over here. You can't really see it. G of 10, 10's off my graph, but I know that this line continues straight based on the arrow that's happening here. So the height of my graph when x is equal to 10 is still -2. Now the last question is, for what value of x is g of x equal to 1? So all you do is trace along kind of the line and wait till it gets to a height of 1, because it says g of x equals 1. Where does it get to a height of 1? Oh, it gets to height of 1 when the x value, for which value of x? X equals -2. It's a different question that this is asking. It's not asking us for the height, it's asking for the x value once it reaches the height of 1. Come on, computer. X equals -2. Okay. All right. That's it for this video. Thanks for tuning in, and we're going to see you next time. You guys are amazing. Have a great weekend.